Physical science is in Chapter 3, Section 2, called The Changes in State. As you'll recall, states of matter are solids, liquids, gases, or plasma, and we're going to look at the changes in these states. We'll focus on solids, liquids, and gases. So we're going to look at the energy transfers when these changes in state occur. We're also going to explain how the law of conservation of mass applies in the changes of state, the physical changes, and the chemical changes. And we're going to look at how the law of conservation of energy applies to the changes in state in the physical and chemical changes. Let's look at our changes in state. This diagram is very important, so hopefully you've drawn it, where we show when a solid becomes a liquid and a liquid becomes a gas, whether energy is absorbed or released, and what do we call the process. Let's start by looking at solids changing into liquids. We call that melting. Melting is when the particles, as a solid, you know that the particles are fixed, which means they're in a fixed location, but they continue to shake. When you melt them, though, the particles of the solid have become, they're still close when they become a liquid, but now they're able to slide past each other. So you can see that energy must be added. That's what those red arrows show. Then when a liquid becomes a gas, we call that evaporation. You got to add energy because those particles need to move independently. Could you write down on your diagram that evaporation is the change from liquid to a gas, but also boiling, right? Boiling in this change. The difference between evaporation and boiling is that evaporation is when a liquid changes to a gas on the top, but boiling is when the liquid changes to a gas throughout the whole liquid. When you change from a solid to a liquid, it's melting. Liquid to a gas, it's either boiling or evaporation, but there's a shortcut. You can also change from a solid to a gas. We call that sublimation. It does not get drippy. For example, dry ice. Dry ice becomes a gas. It never goes through the liquid state. All of these have to have energy added. But what about if we go the opposite direction? When a gas becomes a liquid, the particles have to slow down and they get close together. And that process is called condensation, the changing from a gas to a liquid. Then when a liquid, and you have to release energy to be able to do it. When a liquid becomes a solid, the particles are already close together, but now they go from sliding past each other to being in a fixed position. And we call the change from a liquid to a solid, we call it freezing. Let's look at what happens when you have an ice cube at negative 100 degrees Celsius and you add heat. When you add heat and the water starts out at negative 100 degrees Celsius, what happens to the temperature? You add heat. Does the temperature rise steadily? Turns out something different happens. When you add heat to ice at negative 100 degrees Celsius, first of all, the temperature increases to 0 degrees Celsius, and then it remains constant. And then it increases to 100 degrees Celsius, then it remains constant. And then it increases forever. So why does this happen? Something special happens when you get up to 0 degrees Celsius. When you get up to 0 degrees Celsius, the temperature remains constant because the solid ice that wants to become a liquid when energy is added is changing from a solid to a liquid, and we call that melting point. And so 0 degrees is the melting point of H2O. Then when the water gets up to 100 degrees, it changes from a liquid to a gas, and so that temperature is the boiling point. When water is boiling, it maintains 100 degrees Celsius. It does not get hotter. And then once all the water is melted, then it becomes a gas. So we've looked at what happens to temperature as heat is added to water. Notice that energy can do two things. When you add energy, it can increase the temperature like it does here, or it can change state of matter, like from solid to liquid here. We see that energy can be used to either increase the temperature or to change the state. Let's look at what happens. What is the temperature of water versus time as heat is removed? This time we're going to start with the water at a very hot temperature, 200 degrees Celsius, it's a gas. And we'd like to know if you remove heat, what happens to the temperature? Does it steadily decrease like this? It does not. We have an interesting graph that we get. The temperature For water, water starts out at 200 degrees Celsius, and so it's a gas. Temperature decreases to 100 degrees Celsius, and then it changes from a gas to a liquid. We call that condensation. Then between 100 and 0, H2O is a liquid. And then when it gets to 0, the temperature remains constant because water is changing from a liquid to a solid. And then if you remove heat, after it's all become solid, the temperature decreases. So we see that once again, temperature can either cause a change in heat can either cause a change in state or a change in temperature. When we look at this graph, what's amazing is that it tells us what is the freezing point of H2O. The freezing point of H2O when it changes from a liquid to a gas, we can see is 0 degrees Celsius. So let's look at the definitions of these changes in state. Freezing point, the temperature at which a liquid becomes a solid. Melting point, the temperature at which a solid becomes a liquid. Which one's greater, freezing point or melting point? They're the same. They're both 0 degrees Celsius. Boiling point, on the other hand, is the temperature at which a liquid becomes a gas. So we've looked at these temperatures. Let's consider, we know what temperature happens, what temperature does when it's a change in state. What happens to the mass when we change state? We find out that mass cannot be created or destroyed in a closed system, so when it changes state, the mass remains the same. Let's start with solid ice, change it to liquid water, and then change it to water vapor. When you have solid ice, and let's say we have a 2.0 gram sample, and we melt it in a closed container, we're going to have 2.0 grams of liquid water. And when we evaporate it in a closed container, we're still going to have 2.0 grams of water vapor. So mass is not changed when you change state. What about volume? Let's say I start with 2.0 milliliters of water. When I change solid ice, 2.0 milliliters, and I melt it into liquid water, it actually becomes about 1.9 milliliters. We'll discuss why a little bit later. When I then let it evaporate or boil, and I still have it in a closed container, it has to be 2,500 milliliters. So is volume conserved? No, it is not, but mass is. So when conservation of mass says that when a substance is changed, either frozen or melted or reacted or dissolved in a closed container, mass is conserved, but volume might change. We've looked at when you change state, what happens to the energy. Energy is either absorbed or released. We've looked at what happens to mass. When you change physical states, mass is conserved. Volume is not, but mass is conserved. Let's look at what happens to energy. When you change states, is energy created or destroyed? We find out the law of conservation of energy, which says energy cannot be created or destroyed. It just changes forms. For example, wood burning in a closed container. If we have a piece of wood and oxygen in a closed container and we send a little bit of electricity into it, the wood will burn, but since it's in a closed container that's insulated, energy will not be created or destroyed. It's simply changing form. We've looked at the law of conservation of mass, the law of conservation of energy. We said that mass cannot be created or destroyed. Energy cannot be created or destroyed. Are there any exceptions? In fact, there are. Nuclear reactions. The exception to the two laws is nuclear reactions when mass and energy are interchangeable. This is Einstein's equation, which says energy is equal to the mass destroyed times the speed of light squared. And this is what happens in nuclear reactions. In section 3.2, we've had 3 objectives: to describe energy transfers and the changes of state, and to explain how the law of conservation of mass applies to changes in state, and how the law of conservation. Physical Science, Chapter 3, Section 3, discusses applications of the kinetic theory on fluids. Recall, fluids are those things that flow, so they will be liquids and gases. We're going to apply kinetic theory to the ideas or the concepts of pressure, viscosity, diffusion, and thermal expansion. First of all, let's review kinetic theory. Kinetic theory says that atoms are tiny particles always in motion. The higher the temperature, the faster the particle moves, and at the same temperature, the more massive particles move slower than the less massive ones. Let's look at pressure. When you have a tire and you inflate it with air, That air pushes against the walls of the container because there are many collisions, and it applies a force. And the force exerted per unit area on the surface is called pressure. Wonder what happens if you increase the temperature of the gas inside. Those particles are going to collide with the walls much more frequently and harder, and so if temperature, first of all, the cause of pressure is that particles are hitting the walls of the container. If temperature increases, then pressure increases because the particles hit the walls more frequently. This is an application of kinetic theory to fluids. Next, let's look at viscosity. Viscosity is resistance of liquid to flow. An example would be honey or water. Which one is the most viscous, meaning the most resistant? Honey is more viscous than water. And what causes this? The cause of that is large molecules in honey or stronger attractions that make it flow slower. If we increase the temperature, you guys know what happens. If we increase the temperature of honey, is it more viscous, meaning resistant, or is it less viscous? It's less viscous. So as temperature increases on a liquid, then viscosity decreases. Next, let's consider diffusion. Diffusion is defined as the spontaneous spreading of a gas or a liquid or a solid. They move from high concentration to low concentration. Example would be like perfume in a room. If a room is completely closed and there is no wind or drafts in there, and someone squirts perfume in one side, the particles are constantly moving, so they randomly move around, and we have that natural flow from a high concentration to a low concentration. If we increase the temperature, the particles are moving faster, and so the rate of diffusion increases. We see this happening in water. If you put dye molecules in water, you don't have to stir or anything, and the particles are constantly moving, so they spread out and then they are evenly distributed, and we call that equilibrium. Next, let's consider temperature. Temperature, when you heat something up, the volume increases. That's called thermal expansion. An example would be a thermometer. When those particles get hot, the volume increases, and so the red liquid moves to other parts of the thermometer. What's the cause of this? The reason why the volume increases when matter is heated is because you got faster moving particles. And so if temperature increases, then volume increases. In section 3.3, we've discussed applications to kinetic theory on fluids. We've talked about pressure, viscosity, diffusion, and thermal expansion.